Hello, everybody. I'm sorry about the delay. I was actually in the middle of talking to quite a few people at Carnegie Mellon University, which is a place that I work right now. And the reason is because, as some of you know, I've been working on an app to go and try to help stop the spread of COVID-19. And so there have been some very, very big developments, which you might hear about soon. So there was a meeting that I was at that ran a little bit over. Okay, great. But in that case, I think it's time to go and start talking about math. I love talking about math because I've been thinking about math all day, and I always think about math as I look at any problem that there is in the world, because you can use math to understand it better. Now, if you're new to this live stream, let me tell you roughly how this works. I'm here. I talk about whatever questions that people might have. And these questions range across all kinds of different areas of math, but I try to choose the questions that might have something to do with Algebra 1 or geometry, or that I can tell a story about that is understandable to people who are studying Algebra 1 or geometry. Now, at the same time, these lessons are just lessons from all over different topic areas, and I will intentionally not answer the questions that are just like the things you would learn in school, because you already have a teacher who can help to explain that particular type of topic to you. Instead, I'm trying to give you something that you might not be able to find otherwise. All right. Well, in that case, let's go ahead and maybe start talking about some of these particular questions. What do we have here? So I see, I'm looking at some of these questions. Some of these are very specific questions, which somehow, let me see. Some of these questions are very specific and maybe are not as good to talk about. So, somebody has a question about throwing a stone. I'm curious. So somebody says, at what angle should I throw a stone and make it bounce 3 times? So that's the question. What angle to throw a stone and make it bounce 3 times? I think the question first is like, how bouncy is the stone? Some stones bounce a lot of times. Some stones don't bounce so many times. But I'll say, because every stone is different, I'll tell you what I'll do. So the question that we have here is, what angle to throw a stone and have it bounce 3 times. Okay. And now the reason I'm giving you this answer is that the answer is going to be one that maybe is not what you were expecting. You were probably hoping to get an answer which is like 30 degrees or something like that. But it depends. It depends on the stone. And so the only thing I would know how to do is to try throwing it at different angles with different kinds of speeds and try to figure out which one makes it 3 times. What do I mean? Well, if you start to change your angle, then the amount of energy that the stone is coming down with changes, in the sense that if I throw it more up, then of course it's going to have some energy as it goes up and then comes back down and then it hits the ground. But at the same time, if I use that same amount of energy to throw it straight down, that would actually also have some amount of energy going into the ground. So I think what I'm telling you is that the way I would solve this problem is by trial and error. I would actually go and try first maybe throwing it down at the ground. I might try just dropping it on the ground. I might try, and if that makes it bounce like once or twice or something, I might also try throwing it horizontally to see what happens. But if you think about the mechanics of the stone, I think that the additional extra force that you make it go forward doesn't necessarily help you too much with the bounce, because in the way that this bouncing stuff works, it's that somehow if it's bouncing like this, bouncing towards you, it could just as well have bounced like this. So I think the answer that I would give you is I would just try, somebody says all you need is a flat bottom. That may be the case. I mean, in some sense, what you need is you need to know whether or not that energy can be turned back into bouncing. But I think the answer I'm going to give you is this is what we'd use for the way I'll do this is by trial and error. But I want to tell you why I said that as the answer. Because you see, you can also talk about trial and error if you want to go and try to solve equations. So this question I cannot answer precisely with math. On the other hand, there are other kinds of questions that you can answer precisely with math. So what if I decided that I was curious? Let's ask a different question. It's a math question. What is the square root of 5? So now I'm going to give you a way to do the square root of 5, which is not the most efficient way to do it, but it is a way that could work. What might you do? Well, you might say, could the square root of 5 be 1? Well, if I took 1, would 1 work, right? I could try, does 1 work? And I try 1. If I square 1, I get 1. Too small. Does 2 work? Well, if I square 2, I get 4. Still too small. Does 3 work? 3 squared is 9. Too big. But now I know it is between 4 and 9. So if it's between 4 and 9, now, 5 is between 4 and 9, so now I need to try some numbers in between. What number should I try? Should I try 2.5? If I use 2.5, I get 2.5 squared, and 2.5 squared, 25 times 25 is 625, so I could say that's 6.25. And now I know that it's between 2 and 2.5, because 2.0 squared is equal to 4.00. And since I need to be somewhere in between, then it means I need to choose something else. And so, yes, somebody says maybe 2.2 or 2.3. Let's try something in the middle. What's a nice number to square? I'd like to square 2.2, because 2.2, it looks like my screen froze. Just a second. This happens once in a while. I'll just have to go and close it and reopen. But the good news is that actually it'll give me a clean space that I can write this in. Great. So I'm going to do it here, and it'll be a clean space that I can rewrite this in. And so we were somewhere around, like, between 2.0, 2.0 squared, that was equal to 4.00. We had 2.5 squared, which was 6.25. And if I took 2.2 squared, now that's a nice number. In fact, 2.2 squared is related to 22 squared. 22 squared is equal to 2 times 11 times 2 times 11. And now if I take 2 times 11 times 2 times 11, that's equal to 4 times 11 squared. 11 squared is 121. 4 times 121, which is 484. Okay, so I get 4.84. Meanwhile, I could also try to figure out, what's 2.3 squared. Someone suggested 2.3 squared. I don't have a nice trick on this one, but if I just do it, 23 times 23, 3 times 3 is 9, 3 times 2 is 6, 6, 4, that's nice, 9, 12, 5, 529. So I get 5.29. But what I'm showing you is that we're able to now find out that the square root of 5 is going to be somewhere here. So this is sort of like, this is why I chose to take your question about, what angle should I throw a stone in order to make it skip 3 times? I don't know. But I would use the same technique that I would use to go and try to find out what is the square root of 5. And if I had to find the square root of 5, I could just keep going and keep going. It would be a painful process, but I could actually use this to go and figure out the square root of 5 if I wanted to. So hopefully that's a useful answer, and hopefully that also shows you why algebra is neat. Like, the very fact that I can find out the solution to a quadratic equation without having to guess and check is very powerful. Because if this is all we're using, guess and check, then it's not actually a very efficient way to go and find an answer. More questions. What else can we find? Oh, it's neat. Somebody actually has thought about this, throwing a stone and asking for it to bounce 3 times. And Lawrence Sun says it's around 26 degrees, according to Mark Rober. Maybe that's the case. I will say it does depend on what kind of stone you're using, though. So I'm not sure it's always the same answer. What else do we have? So I'm looking at other kinds of questions. Okay, we haven't talked about geometry for a while. Somebody wants to know how do you find the radius of a circle that is circumscribed around a triangle? Oh my goodness. Okay, let me think if I actually have a way I can tell this to you. This is pretty sophisticated, okay? So let me see what I can do. So somebody says, I've got a triangle. And there's a circle that's around it. What's the radius of that circle? So the question is, given a triangle, how do you find the radius of the circle? I see. So Anonymous Cheetah has some things. So it actually goes beyond the topic of this live stream, beyond the scope of this live stream. This is not what you usually see in high school geometry. But there are some very important ways that you can find the area of a triangle. If somebody told you the 3 sides, which maybe you could measure, this is a real life thing, I'm looking at a triangle, I want to measure the 3 sides, well, there's a nice formula for the area of a triangle. That formula is called Heron's formula. And the area of the triangle can be written in terms of the square root, it's a huge formula, the square root of, you first calculate the semi-perimeter, that's called S. So I'll write where S is the semi-perimeter, A plus B plus C over 2. All right, S times S minus A times S minus B times S minus C. Oops. So this formula is called Heron's formula. It's a nice formula. Philip Neller puts that into quotation marks. You somehow don't think it's a very nice formula. Well, I think it's a nice formula because it exists. And Carlos Torres says, prove it. That's a very great thing to do. I actually did prove it because I was curious how this works. You can actually prove this with the Pythagorean theorem. And in fact, the proof, when I did it, it took me about half an hour to do. We actually ended up putting that proof as a bonus in the end of our daily challenge online course, geometry course. So because that happens to already be in our online course, I won't redo it right here. That online course is not the same as this YouTube daily live stream. We actually, on the daily challenge with Po-Shen Loh, we just have a bunch of courses that talk about all of these kinds of more advanced middle school math, competition math. So that one, yes, there's a proof. You can do it with the Pythagorean theorem. It's not that bad. It's actually quite fun, quite interesting. But in this live stream, I'll just say that happens to be a particular formula for the area. But now there's also more things. You cannot just do this because that's not what you asked me. You didn't, oh, Tony Gao said you saw it too. Yeah, so in fact, if you go and watch that proof, you could go and see that it's not rocket science. It actually just uses the Pythagorean theorem. But now I also want another formula. There's another formula that directly relates to the radius of the circle. So the radius of the circle, let's call it R. Okay, so the radius of the circle is R. And it turns out there's another formula. It uses what's called the law of sines. And so now we have something that's involving trigonometry, which I cannot talk about here because that would be beyond the level of math that we need. But there is something called an extended law of sines. And the extended law of sines, when you apply it to make an area formula, there's another area formula. And it's just equal to A, B, C over 4 times R. So now that's kind of nifty. It's that somehow, no matter what, if you actually have any circle which has a triangle inside, the area of the triangle is just the A times the B times the C divided by 4 times the radius. That's amazing. And now that particular proof, that one uses something called trigonometry, so I won't do that here also. However, at this point, if you have both of these formulas, you can figure out the R. So the original question was, how do you find the radius of a circle that goes around the 3 points if you just had a triangle? And the answer is, just go and measure the 3 lengths, A, B, and C. Now these two things are equal. If those two things are equal, set them equal to each other, and then I'll get a relationship. A, B, C over 4R is equal to the Heron's formula thing. S minus A, S minus B, S minus C. And then to get the R, you just multiply the R up here, divide this thing down there, and you'll get it. And that's going to be the circumradius. That's called the circumradius. So this is more advanced than what we would usually talk about in this particular live stream. But I just want to say that particular proof of this Heron's formula, you can get that straight with Pythagorean theorem. This one's some trigonometry. Put them together and you get the answer. Okay, what else do we have here? Oh, somebody is thinking about these like 4-leaf clovers again. And Eric Feng asks, is a 4-leaf clover farm possible? Well, that's a good question. I guess I don't exactly know how you make 4-leaf clovers, in the sense that I don't know how clovers reproduce. I assume clovers reproduce when there are some flowers, and the flowers make some seeds. And then the question is the 4-leafness something that can reproduce on its own? So that's a pretty good question. The way I would test that is I don't know the answer, but the way I would test that is I would I'll try to find a 4-leaf clover. Don't pick it. If you pick it, then you can't use it. But it's like you just watch it and you try to figure out how it flowers and how it makes some kind of a seed. And then you go grab the seeds and you try. And Temp ID actually has the emoji for it with a 4-leaf clover farm. What else can we have here? Okay, so I see some problem that uses some math calculations. I'm a little bit curious about this one, so let me see what happens. All right, I'm going to try to read it as we go. So a screen is 1,000 by 500 pixels. All right, we'll draw a screen. Here's a screen. 1,000 by 500 pixels. Like maybe it looks something like this. 1,000 by 500 pixels. And a subscribe button is 50 by 100. I'm guessing what you mean is that the subscribe button what does that look like? So the subscribe button would be 50 by 100. So presumably it's like somewhere here. And you mean it's like 50 like this. And 100 here. Okay. And a cat moves the mouse 5 times and then clicks. And each movement is 250 pixels. What's the probability of subscribing to Po-Shen Loh? Oh, that's interesting. So somehow a cat's going to move the mouse, and it's going to move by 250 pixels, and then 250 pixels, and 250 pixels, and so on. And you move, like, how many? 5 times, 5 times. So if you move 5 times with this kind of motion, so if you move 5 times with this kind of motion, the question is, what's the chance that you actually land on that piece? So I would say, yes. Where does the mouse start? I don't know. I thought there was a cat. Ah, I see. So oh yeah, the cat would eat the mouse. It looks like Wei Gu figured out the joke. But in any case, this is somehow, yes, there's an actual, the cat is using a computer mouse. Using one of these, right? Using a computer mouse, right? And using the computer mouse to go click around. And what you need to know is, for example, where does the mouse start? For example, if I look at this picture, it's like, well, 1,000 pixels. Maybe that's why the person chose to move 5 times. If you move 5 times, then presumably after you move 5 times, you could be, just as likely to go anywhere. But we do need to worry about like where you start. Because even if you move 5 times, if you started all the way in that top corner, and if the button was all the way in the bottom corner, the answer is 0. So I'll say it depends on actually the question depends on whether or not the mouse pointer is starting in one place. How did the mouse get on there, right? But let me answer it in a different way, okay? So the different way I want to answer it is, this is a pretty nifty question. And I wonder if I could answer the question if it wasn't about the moving the mouse 5 times. What if the cat moved the mouse randomly 5 million times? Well, this would be a very bored cat by the end. But what I'm trying to say is that it's hard to actually answer the question if you only move like once, because then it depends a lot on where you started. And then it also matters if you move it like twice, or if you move it 3 times, because you might not be able to go across the whole screen. But what if instead I changed the rules, and I said that this mouse has just been moving around like crazy, and it's been moving around and moving around and moving around like 1,000,000 times. Now, in that case, the real question becomes, if you have moved this all these 1,000,000 times, where is it likely to be on the screen? And if you want to do a probability question, you basically look at the likelihood that it ends up in this rectangle divided by the likelihood everywhere. And now this is an interesting problem in and of itself. So here's a new problem. Suppose I just have my 1,000 by my 500 screen. That's my screen. And suppose I do this random move, 250 pixels at a time. So now the question is, after you've moved 1,000,000 times, let me ask everybody, is it more or less likely to be very close to the corner versus somewhere in the middle? Can anyone answer that question? So the question here is, you're moving this mouse. You're moving 250 pixels. And over and over and over and over and over again. 1,000,000 times. So after you've done this, so some people are saying symmetry. What was the question? Thank you very much for asking. The question has turned into, I have a screen, 1,000 pixels by 500 pixels. I have a mouse pointer, which is randomly moving 250 pixels as a jump, 250 pixels, 250 pixels, 250 pixels, and it's just going to jump around the screen 250 pixels at a time. And now the question is, and so like as it's moving around this 250 pixels at a time, the question is, what's the relative likelihood of it landing in the close to the corner versus somewhere in the middle? And I'm actually going to ask this question: how much more likely is it to land in the middle versus very close to the corner? And how might you even think about that? So I'm talking about the relative likelihood of likelihood. Well, yeah, it's not really likelihood. It's a probability distribution, but the likelihood of ending here versus here. Does anyone have an idea of what the ratio should be? So many people are right that somehow you're more likely to end up somewhere in the middle, right? Oh, wait. It's also complicated. Actually, this is becoming a very interesting problem. So the interesting thing is that Oh, wow. So this is actually a very interesting thing. So it's far more likely to land in the corner, but for another reason. It's because as you're moving around on the screen, if you move towards the corner, what happens to your mouse? It just kind of gets stuck in the corner. So in fact, if you're moving your mouse and you're moving your mouse 250 pixels, you're actually quite likely to end up in the corner. So you know what? I want to make the question like this, okay? I'm going to say the question is that every time I will move less than or equal to 250 pixels. I want to have some kind of a model, okay? And the model I'm going to say is that you choose, I think this will be enough for me to specify the problem. So here's what happens. At every moment, your mouse pointer is here, okay? So you're here. And what, oh, that's supposed to say here. And now what you do is you're going to choose a random point that's inside this circle of radius 250. And you choose a random point in that circle where everything has, I want to say inside the circle, okay? So it's a circle of radius 250, but you choose a random point anywhere in the circle where it's called uniformly distributed, in the sense that you're just as likely to be anywhere inside, okay? So we're going to say that you're starting here and you can move anywhere in there. However, there's a catch. If you actually started up here close to the top, okay, if you started close to the top corner, you know what happens to that square? Sorry, what happens to that circle? That circle looks like this. And since the circle looks like this, if you were supposed to fall off the end, what would happen? Well, if you were supposed to fall off the end, you were supposed to go all the way there, and you don't. Instead, you kind of stop there instead. Does that make sense to people? So in some sense, if you were supposed to go off the edge, and let's do another example which is more clear. If I was supposed to go off the edge, let's pretend I was supposed to go off the edge this way. If I was trying to go to that, if I was trying to go all the way off to that part, what would actually happen is I would go that way until I got to the edge, and then the last bit, I would go kind of along the edge a little bit. I don't know if you see my little tiny stub here. I'd go along the edge a little bit, and then I'd stop. So the place that I'd stop would be wherever that is, and just kind of pull it down a little bit, because it's like I tried going towards there, but I didn't get all the way. What if the screen is a torus? Well, that would be like our game of asteroids last time. But this is going to get pretty interesting, because now we're going to get to analyze something, okay? So the model is simple. It's actually quite realistic. You start with the mouse pointer here. You're going to move it into some random position, which would be up to 250 units away from you. And, you know, if you were going to fall off the edge, it just kind of goes along the edge and then continues going a little bit until wherever you were supposed to stop. So now let's get a new picture. Now, I'm going to look at a big picture. Here is the screen. Okay? Now I want to know something about the relative likelihood that you end up here in the middle versus on the corner. And the way you think about this is, how do you get there? See, we're talking about relative likelihood after you've done this a million times. After you've done it a million times, it does something called mixing. So this is actually a notion in probability theory, which is that, you know, if you just do it one time or two times, it depends very much on where you started. But after you've done it like a million times, we're doing geometric probability, but after you've done it like a million times, if I want to know how likely it is that I'm going to end up at that point, relative to other things, well, I'd say, how do you end up at that point? The way you end up at that point is if you were in any of these places. Oh, I'm trying to think, what's the most efficient way of saying this? So the way you'd end up at that point is that, you know, you kind of undo the motion that we just did, and you could have gotten to that point from any one of these points. Does this make sense to people? So somehow, like, how could I have gotten to that point? It's like I could have picked anything here. Actually, I'm now starting to realize I do want to go back to the thing where I move exactly 250, and the reason is because it'll be easier for me to explain something to you. Okay? So I'm going to switch into the one. I'm going to switch back into the model where you move exactly 250. That's going to be important. Let's go back here. Let's erase the less than or equal to. That's important. And so now what we're doing is we're going to choose a random point on the edge to go to, because that's going to help me do something easier. Now when I go here, I can say, all right, what's the likelihood that I'm going to end up on the point in the middle? Get rid of all this stuff. It's somehow I can only get to the point in the middle if I started from one of those. Does that make sense? So I have to start from one of these points, and each of those is kind of equally likely, and then I could get to that point. Now here's another question. How could I get to the corner? If I wanted to get to literally the corner. Oh, you can't see the corner. Here, big point. Bigger point. Okay, if I wanted to get to the corner, how could you get to the corner? Now, getting to the corner, you have more choices. You see, I can still draw the quarter circle. If all I did was draw the quarter circle, I would say, oh, it looks like you're 4 times as likely to get there as you are to get here, because you have like 4 times as much circumference that you could use to get there compared to getting here, right? Seems reasonable. Like, it's like, look, there's 4 times as many points. It's not really you're counting points. There's something called measure theory in the end where you count the measure. But here, even if you're taking geometry or algebra, you can understand. It looks like there's 4 times as likely. There's like 4 quarters there as there are there. But there's a catch. There's a catch. The catch is that actually there are more ways to end up into this corner. If you started on any of those points and chose the direction to go in the corner, you could. However, you can actually also go into the corner if you, for example, started here. If you started there and you chose a direction that was in the right direction, meaning if you were choosing here and you were trying to go like there, you'd also end up in the corner. Does that make sense to people? So it's actually not it's actually not true that you're 4 times as likely to get there. In fact, once you take into account the different directions you can go in, you are far, far, far more likely to get into the corner. Because in fact, every single one of these points, there's a range of, how do I point here? Because my thing is backwards to yours. There we go. Oh, this way. There's like a whole range of directions that you can point in that will get you to land into that corner. Did that make sense to people? So somebody says that, no, you're confused. Let me explain again. So Jacqueline, so let me explain it this way. And of course, I didn't mean to call you out just by name. There's lots of people. Whenever there's one person who says they're confused, lots of people are confused. All right? So the deal is, any point on this circle could have made you go to that corner. But here is something else that could make you to go to the corner. If you were here and you tried to move like this, if that was your 250 pixel move and you were there, you would go to the edge and track down into the corner. So the point is that there's actually many, many other ways to also land in the corner. In fact, this is what we call a one-dimensional set of ways. There's only like this one circle. Just the points on that circle over here will get you to land on that particular number. On the other hand, when I look over here, there's like lots and lots of different points from which I could end up in the corner, because I would try to move my 250 pixels and I would kind of fall into the edge and crash into the corner. Did that make sense? I'm trying to say that there's a lot of different ways that you could end up in that corner, whereas there's only a few ways that you could end up on this particular point. And now, when I look at this picture right here, like all these points inside could actually take me into the corner. So the main point here is to say, when I have this particular situation, you're much more likely to end up into the corner than you are to actually end up in any particular other point that's elsewhere. People are saying it's confusing. Maybe it's confusing because we have something that's involving, maybe it's confusing because we have something that involves all of these different two-dimensional things. I wonder if it would be easier to understand if we did everything where we're just walking on a line. Yeah, I think that would work. Let me explain it to you this way. There's a much easier way to understand what I just said. We'll turn it a lot simpler. But by the way, my conclusion from what I just said is that if the button's in the corner, you're more likely to land there with this random motion, because you're much more likely to land in the corner than you are to land in any other particular point. Oh, although the button does have area, so I'd have to take that into account when I come here too. Okay, but maybe let me roll into a different mathematical question, which is going to be easier to model, and maybe then people will understand this better. Here, one dimension. So what I have now is I just have a line. And the line on this side is 0, and on this side is 100. And what's going to happen is that as you're on this line, you're always going to be taking a step of, oh wait, let me not use 0 and 100. Let's use 0 and like, oh no. That's actually not going to work well. The reason that's not going to work well is I even wanted to have something where you can have a part of a distance that you can move. So maybe let's not do this. Let's not do the line, because unfortunately I cannot. The problem with the line is that if I start moving by specific amounts, then where you are on the line jumps between particular places. So I think we won't be able to hit the line on this one. But let me then just use this to wrap up this particular piece, which is to say, you've probably noticed this too. If your cat or whatever is moving a mouse around, it somehow is quite likely to land in a corner. And the reason is simply because the corner captures it more likely. Like somehow you can hit against the edge and then still land inside the corner. And that's how I'd answer this question. All right. What else can we do here? And again, please understand, like you could do like very, very carefully. However, based on the number of people who say they don't understand, I think it's probably better that we don't focus on this topic for the live stream. Okay, what else do we have? Wow, I'm seeing science questions appear here too. So yeah, okay. So I see. I mean, I see. There's some science questions here too. It was supposed to be a math live stream. I'll just quickly take one. Somebody asked, like, why does yeast rise in bread? The reason is because it has to make bubbles, right? That's what the bubbles are in the bread. That's what makes the bread easier to eat. But if you want to make bubbles, you got to make some gas. And what yeast does is, I believe, it makes carbon dioxide. The point is, all of us, I mean, a lot of life works by getting some energy from some sugars or something like that. And then after we digest those, we turn those into carbon dioxide. Well, we make carbon dioxide as one of the outputs. And yeast is something that will take the sugars that are inside your mixture, or the starches in your I think it's sugars, in your mixture, and then it will turn those into, it will create carbon dioxide, and that happens to be inside the dough, which helps to make it rise. So it basically is like, yes, you've got to make a gas somehow. And fortunately, you've got all of these like little yeast organisms, actually, which are all throughout your mixture, and they all happily make some bubbles for you. They make some carbon dioxide for you. If you think about it, it's actually quite interesting that such a thing would work. It's like, I need to have bubbles everywhere in my dough. How could I make bubbles everywhere in my dough? Can I just go and dig a lot of holes? That'll take me forever. Oh, what if we have these tiny microbes called yeast, and those microbes even reproduce? They even make more microbes. So they kind of grow throughout the whole mixture. And then, as they go and try to digest the sugars inside the bread, they will all make little bits of carbon dioxide, and you've got all of this, all of a sudden, this nice bread to eat. It's kind of neat if you think about it. Okay, what else do we have? Aha, so somebody has a math problem that has numbers. Let's go there, because it seems like this particular geometric thing might be a bit too hard. Let's go to a math problem with numbers. So somebody wrote down this question. They said I should take 1900 plus 73, and this is John Liu, cubed minus 1900, 79, okay, just a second, minus 79 cubed minus 1900 cubed minus 79 cubed divided by 1900 times 79 times 1979. What? You want me to do that? That looks terrible. Why in the world do we want to do that? John Liu, you're going to make me do a huge calculation in front of everybody? I mean, I don't know if I even want to. I can add 1979. I can do that part. That's 1979. But I see a 1979 there too. So my hope is that maybe there's going to be something that cancels. You see, I see that number, and I see that number. Actually, I see a lot of patterns here. I see a 1900, I see a 1900, I see a 79, and I see a 79. Whenever I see anything with repeated numbers like this, let me tell you what I do. I'm lazy. I don't want to do any calculation unless I know what I really need to calculate. And so the first thing I would feel like doing is I'd feel like trying to expand, I'd feel like trying to write this out with like A's and B's. So let's see. Suppose I let A be 1900 and let B be 79. So what do you really want me to do? You want me to do A plus B cubed minus A cubed minus B cubed divided by A times B times A plus B. Okay, if that's what I'm supposed to do, I think I should maybe try to figure out how to open up the A plus B whole thing cubed. Oh, I see. Some people also wanted me to talk about the binomial theorem. That's already one of the topics in the classes that I teach in the daily challenge, so I don't want to redo that one right here. On the other hand, we can just, I don't want to do the general binomial theorem here. On the other hand, we can just open up A plus B whole thing cubed. That doesn't take so long. What do? Let's figure it out. If I want A plus B whole thing cubed, that is A plus B whole thing squared times an A plus B. So let's start with A plus B whole thing squared. If I want to expand out the brackets, then that's going to be A squared, because I can take the A from here and the A from there. I also have an A times B, and I have a B times A. So that would be plus 2ab plus b squared. Is everyone with me here? Like, all I did there is I took the a and the a, got the a squared. I took the b and the b, got b squared. And I took the a and the b and the b and the a, and that made 2ab. Okay, I see some people already figured out the answer. But now let's do cubed. If I need to do cubed, I need to take a squared plus 2ab plus b squared, and then multiply it by another a plus b. What might that look like? I wonder if I have space without running into my head. Let's try. If I took the a squared plus 2ab plus b squared, that's a plus b whole thing squared, times another a plus b, now that would give me a plus b whole thing cubed. How do I do this? I need to take all the ways of picking something from here and something from there. So what's the easiest way to do this? Let's just try. Oh, I have an idea. I'll do it the way that some people do in other countries, which is a little bit easier for me to write. I need this a squared plus 2ab plus b squared and an a plus b. So I'll write a squared, 2ab, b squared against a plus b. So as you can see, what I'm going to do is I'm going to write down in each of those locations what it is when I multiply the thing that's labeling the row and the thing that's labeling the column. And so I'll get an a cubed here. I get a 2a squared b, and I get an ab squared. All right, I'm basically saying this is a times the b squared, so I put it there. Over here I have a squared b. Oftentimes in math, we like to write things alphabetically, so I could have written b a squared, but that's the same as a squared b. Over here I have 2a b squared, and I have b cubed. Okay, what happens if I try to add everything together? Oh, this is nice. When you add everything together, a lot of stuff will join. Not cancel yet, but join. So when I add all this stuff together, I get that a squared plus 2ab plus b squared times a plus b is equal to, I have an a cubed, plus I have a squared b and a squared b are both here, 3a squared b, plus 3, it's ab squared, plus b cubed. Okay, so now if I know that, let's put it back. Let's put it back into what I had before. If I put it back into what I had before, then the first part becomes a cubed plus 3a squared b plus 3ab squared plus b cubed minus a cubed minus b cubed all over ab times a plus b. Okay, now if I look at this, life is good because I see some stuff canceling. A cubed, that looks like a hockey stick. A cubed and a cubed, those cancel. That's nice. At the same time, the b cubes also cancel. So at this point, I only have the stuff on top. And now things are looking even better. Because the thing on top is 3a squared b plus 3ab squared all over ab times a plus b. Now this makes me very happy. The reason this makes me very happy is because ab times a plus b is just a squared b plus ab squared. Looks like the top. That's equal to 3a squared b plus 3ab squared divided by a squared b plus ab squared. And so that's just 3. So this is wonderful. This is wonderful. So I actually didn't even need to know what are a and b in the first place. And so this is nice. Actually, I'm done. The answer is 3. It's all over. The only one place to be careful is if you're ever doing a question like this and you say, I'm done, it's 3. At least make sure you didn't divide by 0. So that's where you need to go back and say, just a second, is there anything here where I might have divided by 0 when I was canceling something? Well, no, because I actually know that the a is 1900 and the b is 79. And so the bottom's not going to be 0, and none of these things I'm dividing by are 0. So it's nice. The answer is 3. Oh, the answer is 6. You're saying the answer is 6. Oh, no. So let's double check. So the good news is that if there's somebody here who has a calculator, you'd be able to double check for us and we would know the answer right away. But if I look at this thing again, I would double check my work. It looks to me like it's actually going to be 3, in the sense that I didn't do anything wrong here. This is actually the binomial theorem. The coefficients are 1, 3, 3, 1. And I subtracted off those two ends. So it should be 3. I think we're good. And the beautiful thing is I don't care about 1900 or 79. It's just 3. So thank you, John Liu. That was a really nice question. What else can we do? Oh, wow. So these are interesting. There are two questions that maybe those will probably be the two questions I finish with. The first is, what is a line of best fit? I was just thinking about that last night because there are some things that I'm doing for the Novid app that I need to know this line of best fit. So let me maybe tell you a little bit about a line of best fit. Here is a bunch of points. These points, by the way, correspond to measurements. These are measurements. As you may know, just a second. Great. So these points are somehow measurements. And something I was just thinking about today is that as you build these contact tracing apps to go and find out if anyone else has been near other people, too near other people, the hardest thing to do is to try to figure out from your sensors on your mobile phones how far away are other people. And so we might have two kinds of axes. And these are not actually the axes. I'm making it simpler so it's a line. But you might have some kind of an axis which is over here, which is measuring like, I want to call it some function of signal strength, but that's not going to be nice. So maybe that's not the best way to say it. Let's see. Let me not talk about signal strength or detecting people. Let's talk about something else, which is called like, I've been looking at a plant growing, and this plant is growing, and somehow the plant seems to grow at the same number of inches per day. That's probably better. Okay, so this is time. This is like days. And this is the height of the plant. So now the situation is, as you're measuring this plant, first of all, sometimes your measurements are a little bit off. But I mean, it's a little bit of a strange thing if the plant got shorter. So maybe I drew a bad picture. Let's at least get rid of the things where the plant could apparently get shorter. This is probably good enough. This data looks quite reasonable. And suppose this is what I measured as the days went by. How tall is my plant? Yes, it should never get shorter unless there was like a cat which was eating some of it. We already saw a cat in today's live stream. But anyway, so if you have this particular growth of a plant, and if it's thought that the growth of the plant is what we call linear, then you want to try to draw a line. But it's not very useful to say, here, I am sure that the way that my plant grew, it did this. That's kind of jerky. I don't think that's quite right. The beautiful thing is there's an undo here. Okay, I can undo this. And instead you want to say, maybe you didn't measure exactly right. I mean, come on. Plants aren't always perfectly straight. Maybe it was kind of like wilted a little bit, or maybe the sun was over here, or there was a window. So what you want to do is you want to draw a line of best fit, which is a line. You want a straight line that goes not through all the points, but as close to all the points as you can. Now, at first it looks like this is a hard thing to do. Like if you want to go and figure out how to get a line of best fit, like what would you do? Just kind of try? What does it even mean to be making progress? It's like the throwing the stone. How would I know if I did a good job? Well, I'll tell you what people use to go and try to figure it out. They actually want a line of best fit to be the line, so that if I look at all of these errors, here I'm drawing all of these errors. The errors are saying for every single point that's not on the line, it's like how far off was I? How far off are you is like a vertical. Okay? So actually it seems like it might be nice if you can make a line for which these errors are as small as possible. But what do you mean by make errors as small as possible? Like if I try to put a line in a certain way, I can make it so that the error on this point is 0. Just make the line go through that point. Right? But that's not necessarily interesting. Why is that point so important? So instead what people do is they try to say, I'll look at all of these errors, combine them all, and get a score that says how good is the line. And in fact, the score that we use is the sum of the squared errors. Minimize the sum of the squared errors. So now that seems like a strange thing. Why would I do the sum of the squared errors? Why not just do the sum of the absolute values of the errors? Well, it turns out that the sum of the squared errors is very nice for using something called matrices to go and find an exact solution, to go and find out what is the equation of that line. So there's something nice about when you use squares that you're okay. And I'll tell you a little bit of a reason why squares are nicer to work with than absolute values. Like you might say something like, a line is good if somehow the sum of the absolute values is as small as possible. But absolute value function is not actually something that works with plus, minus, times, or divide. The absolute value function is a V shape with a very sharp V on the bottom, a point on the bottom. And it can't be made by just doing plus, minus, times, and divide. Whereas the squared function is just called multiply the number by itself, and it's always going to be positive. And so you could actually use the sum of the squared errors to go and measure how far off you are. And that would be the line of best fit. So if you want to know how to do this, that's the subject where you use what's called matrices to go and figure this out. Okay, so that was a good question, and in fact I need to do it. In fact, I was even looking to see, are there people who have already done this before that I can just go and implement the source code? That'll be a little bit faster. And it turns out that it's not a crazy calculation, but there is actually some calculation behind it. Okay, and maybe the last question I'll finish with is, Andrew Zhao asked, how hard is rocket science? It's funny, you know, how we call it rocket science, right? Like some people say things like, oh, you're brilliant, you're like a rocket scientist. Well, so rocket science is something that became very much a cool thing, maybe in the 1950s, 1960s, because at that time the United States and actually lots of the rest of the world was fascinated with rockets as being like the frontier. I mean, that's how you got off of the Earth, and that would be like the final frontier, right? So to me, even the phrase rocket science, what that reflects is it reflects people trying to say, let's go for a moonshot. Oh, look at that. That's another one of these words, where you go and say a moonshot is something to reach towards. And so rocket science, moonshots, all of these are referring to things which are very hard to get to and hard to find. And so people have associated that with things that are very hard. How hard is it actually? Of course it's hard. Something that's hard about it is that once you launch something into space, you can't be like, oh, let's go and change it now. It's already there. So somehow whatever you've chosen to do better be done well. You can't be like, hey, we just launched the Apollo mission, or we launched some rocket, and oh no, we forgot to give them something. What are you going to do? They better have it, right? So that means that you actually have to be very careful. That would be something that makes rocket science hard. Also, of course, rocket science involves putting a lot of energy to push things very, very far. Once you have a lot of energy, it's like one of these things where if it's directed in the wrong direction, you can have very catastrophic consequences. So that also makes it hard. Actually, if you find any of these things interesting, I encourage you to get into learning about physics and get into learning about engineering and get into learning about all of these things, because ultimately combining your math with all of these things is pretty interesting. It looks like we actually still have time for one more question, so let's just keep going. Oh, okay, I see. Somebody asked, is probability percentage? Andrew Zhao asked, is probability percentage? What do you use to say a probability? A probability is just the likelihood something is going to happen. And so a probability is actually just going to be like, if you do like an experiment, oftentimes this is equal to the number of favorable outcomes, the number of things that count, divided by the number of outcomes. And that's what people do with what's called discrete probability, when you can count how many outcomes there are and when you can count how many of them are favorable. But the important thing to note is that the probability never gets more than 1. And probability is a way of expressing how likely something is to happen. So the probability, no matter how you choose to define it, it's always going to be something which is between 1 and 0. And a lot of people will sometimes use percent to go and describe a probability. And the reason that percent works is because it's just not so efficient to tell someone, the probability that this is going to happen is the square root of 2 divided by pi. What's that? What's the square root of 2 divided by pi? Probably close to half. I think a little bit less than half, because square root of 2 is 1.4-ish, pi is 3.14-ish. So I would say square root of 2 divided by pi, that feels to me like around 45%. Actually, I'm kind of curious. Is there anyone here with a calculator? I would guess that it's around like 40%, 45%-ish would be the square root of 2 divided by pi. What can you say? Well, actually, is there someone with a calculator who can help me out? I'm actually quite curious. Square root of 2 divided by pi is not going to be 50%. And that's because both are weird. Are you serious? It's 45.01%? Oh, wow. Okay, so I guess the estimation was not bad. So I was like, it feels to me like about 45%. But you see, 45% makes way more sense to you than saying square root of 2 divided by pi. Square root of 2 divided by pi gave you no useful information. You were like, exactly how likely is that? I don't know. It's a weird number. 45% on the other hand, you'll say, oh yeah, I know what that feels like. I know what 50% feels like. It's like a coin flip. And it's a little bit less than that. So that is why people use percents. Because if you were going to say a number and you tell the number in these weird ways like square root of 2 divided by pi, maybe that's accurate, but unfortunately that's useless for most people. On the other hand, if you go and say, hey, the probability is this percent, then people immediately get a feel for it and they say, I understand you. So it is not that probability is a percent, but it is true that many people use percents to express probability to make them easier to understand. Okay. Well, I hope that that was interesting to you guys. I see that we somehow have our very stable audience of about 236, 234 people still here towards the end. As I'm always going to say, please do try to tell more people. This is a very, very interesting community here. I get to see interesting people. We get to have an interesting chat. It looks like you guys are enjoying chatting with each other as well. And we're very happy to be able to leave the chat on because I feel that somehow in this time, it is useful to have a community. If you know anyone who might benefit from joining, please do help share the word. Tomorrow is going to be Friday, and so that's going to be the last live stream of the week. I hope that you'll have a good Thursday, and I'll see you tomorrow.